Great to be here. My name is Maria Roldin. I work for a private consultant company called DHI. And I'm here to talk about how digital transformation changes the way we work with water. And to exemplify that, I have picked one of our recent projects called Future City Flow. It's a project where consultants, water utilities, and research institutes have been working together to create a platform for decision-making and strategic planning of wastewater management. And I have also included a live demonstration of this decision support system. I cross my fingers that it's going to work. So here's the basis. Digital transformation in our society and in the water sector, it fundamentally changes the way we work with water. But in what ways does it change? Well, first of all, we're able to solve more complex solutions. Given that we have more data, we can create solutions to more complex problems. And this is what we try to do in our daily life. But the new technologies, they also lead to new ways of working together. And as you will see, for us, they have led to closer relationships between water utilities and researchers and engineering consultants. The solutions we build are designed and built together. Customers become co-creators, research institutes become innovation partners. And these 2 points I will explain a little bit more in the 2 upcoming slides. This is the first bullet point, the way towards solving more complex challenges. Let's see if I can make use of this. Yeah. So at the bottom line here, this is the value created with the data, and this is time or amount of data. And in the beginning, we're here using data in a descriptive way to describe our system. This is basically what we do when we set up a model, when we calibrate it. Then at the next level, we can use our data to diagnose and analyze our system. Where do we have bottlenecks? What is the capacity of our system? And further up, we have data helps us predict stuff. And this is how we quite often use models today. And Lena, where are you? You showed us an example before where we say, okay, what will happen to our system in the future? What if the climate forcing changes, like the rainfall intensities increase? Or what if we have some sort of disruption to our system? We can predict that and make forecasts, and sometimes also follow our system in real time. And then even further up, and that's where we're going right now. This is where we're using the data and the models in a prescriptive way to help us make informed decisions. And even further up, perhaps even letting the model decide for us in some sort of artificial intelligence way. And I think this is also perhaps where we want to be in a situation that was described by Steve before, where we have to adapt to the failures we know will happen. And we have to respond quickly, and we also have to be able to find the most optimal solution. But this also requires another level of involvement from all people who are touched by this. And just quickly show how we work with innovation at DHI. First, we have research, where we transform resources into knowledge. Then development, where we transform the knowledge into technology. And the final and very important step, innovation, is where technology is transformed to value for society and for our customers. And these arrows aren't, they aren't strict. The universities, they usually come in here. We have research together with universities, also development of new technologies. And our customers, like water utilities, for instance, they are innovation partners helping us out during development and innovation. But you could, in many cases, you could actually stretch these areas out in both ways, because we're working together all way along. So where does this get us? Well, the example that I wanted to show you today is called Future City Flow. It's a decision support system, also for optimizing our system, and it's focused on wastewater systems, so the wastewater flow in our cities. And there are two main goals here, so to say. One of them is we want to use the system capacity as efficiently as possible. If we have a lot of water, we don't want all of it to end up in one part. We want to be able to store water in all our system. And the second part is about reducing the amount of water. So how can we reduce the inflow and infiltration, or tillskottsvatten as we say in Swedish. And for those of you who have worked with this, you know that it's quite often an ongoing project. You keep improving, and sometimes you see changes, but sometimes you just keep getting more and more water in your system. So for the system capacity, we use some sort of real-time control measures, control strategies that show us, that basically make a forecast of the upcoming 3 or 5 days using weather radar or similar rainfall forecasts to predict the amount of water and the flows we will have in different parts of our system, and then using control strategies to try to even out the flows so that we have as little combined sewage overflow as possible, so that the discharge that comes into the wastewater treatment plant is smoothed out to improve the treatment of the water. And then for the inflow and infiltration reduction, we have a simulator where you can test various strategies to see what if I make this, what if we perform this action on this catchment? How much will it cost, and what effects will it have? And it's this second thing here, the simulator, that I'm going to demonstrate for you now. Da-da-da. Here it is. So this is the city of Trollhättan. It's a bit east of Gothenburg. Northeast, I think. Upstream, yes. And what you see here is a map showing the inflow and infiltration to the system in color codes. This here is the fast runoff in the system, so the red areas are the ones that are most affected by fast runoff. This can be changed. So here it says fast runoff, and then I can change to see, okay, I have, in these areas, I have a lot of groundwater infiltration, for instance. And this is today's situation. It's what we see here, dagens situation. And to the right here, we have some meters that show us the percentage of additional water from inflow and infiltration, 70%, so quite high. 1% is going to a combined sewage overflow. This is for a normal year. You can also select a wet year. And 55% of the water is just partially treated at the treatment plant. So basically, it bypasses part of the biological treatment. And this can also be simulated directly here. So basically, you can click here, say add measures or actions, and then you can pick what you want to do. Do I want to create a separate sewage system for stormwater? Do I want to remove illegal connections or reline? Or do I want to introduce blue-green stormwater systems into one or more of my catchments? And then you can select your own combination of measures. And click this play button here, and it takes about a minute to run for a whole year. I have already prepared some scenarios for you. So just to show you what it looks like, here I have, for instance, blue-green systems in all combined areas. Then we see that these change color, some of them. And for planning and decision making, we have this bottom graph here that shows us on the x-axis, it shows us the relative benefits. So if it's a 50% decrease in combined sewage overflow, it will end up at 50% here, for instance. And on the y-axis, we have the cost, and these are based on default costs that we have set up together with our customers, but they can be altered by the user. So what we see here are the four, we have today's situation down here. We have zero cost, but also zero relative benefit, right? And the active scenario, which is the blue-green systems in all combined areas, it's the one, I don't know if you can see it, but there's a slight gray border around it. So it's this one. These three, the green one is the amount of additional water corresponding to this one. So we can see instead of 70%, we have 69. Slight improvement, but not a lot. We have the combined sewage overflow decreased to 0.6, and we have the partially treated water here. So not much change at all. The cheapest one is this one down here. It's the remove illegal connections. And the most expensive one is up here, and I think that's a separate sewer system. And you can also change here. There are two levels of bypass at the wastewater treatment plant. So in intermediate flows, you can bypass the biological treatment, and for really high flows, it also bypasses some of the chemical treatment. So if you want to look at that instead, it's this option here. And you can see the dots, they move accordingly. So what we wanted to create here was some sort of, we're working our way towards a game feeling where you can actually, you're allowed to just play around and try various scenarios. And a bit like you said, working together to try to, in a fun way, find optimal solutions to a problem. There's, of course, a lot more to show around here. We have real-time control feature here. You can compare, like benchmarking here, you can compare your status to other municipalities. How are they doing? Where am I in this list? There's a strategic planning tool to plan in time when you want to put in your measures, some sort of a budget tool. And a lot more. But I think this is what I have time for. So I'm just going to show quickly all the partners that we've been working with here. And that was it. Thank you.
Amazing things that we can do when we work together. Some questions for Maria?
A very simple question to start with. How do you deal with the different beneficiaries? Because the beneficiaries of the improvements are very, very different for each scenario.
Yes. Well, I would say the main beneficiary here is people working with a wastewater treatment facility. So they have been involved in developing this, and they have also been like our main target. The main, in this simulator, the main components we're looking at is how well can we treat our water at the treatment plant, and how can we discharge as little combined sewage overflow to our receiving waters as possible. other beneficiaries, like you're talking about the greater society, or yeah, not really included at the moment, I must say. But this is also intended to be a communications tool. So to easily explain what we're doing to other people, and also then get them to hop on the train with us.
So if you were to do this for a new city, these are hydraulic models that you're running based on the flows you got from the city. Is it easy to pick up the game and go to a new town, and how long would it take to make it relevant for them?
It depends a lot, depending on how much they have done beforehand. But I would say, I mean, given that we have all the measurement data we need to calibrate our models, I would say we could be up and running in a few months. Yeah, something like that.